Hello, everybody. This is Carl's, your friendly neighborhood violin teacher. For my part of the Mathematics PD, instead of looking at professional development from a pedagogical perspective, I wanted to look at it from a student's perspective. So I thought we could investigate a potpourri of three interconnected phenomena in mathematics: sets, large finite numbers, and infinity. When I say student's perspective, here I mean in the sense of a person who is not familiar with the material being introduced, not necessarily a student in the NMIS age range. So I tried to find material that I found especially interesting and hopefully material that you all aren't familiar with. I selected these three phenomena to look at because together I think they represent a huge slice of the diversity of mathematics, and even though they aren't super challenging conceptually, they actually aren't usually taught until kind of upper level math courses in college. Anyway, so to begin, I thought, well, let's look at how all the real numbers are organized. And I mean, that might be a little familiar, but I thought we should start on kind of comfy ground before it gets weird. So you can see here we have sort of three big parts: all the real numbers, big numbers, and many infinities. So let's start with all the real numbers. So we begin, of course, with the natural numbers, and you can see here we can start with 0, but we usually typically start with 1. And the natural numbers, of course, as you may remember, are the numbers we use to count. 1, 2, 3, 4, etc. You can't start with 0. Excuse me. If you start with 0, then you usually call this collection the whole numbers, but the natural numbers works very well. And I want a quick side note here. As you can see at the bottom, I have a little star that says, to get an imaginary number, multiply any real number by I. So what that means is we're only going to be looking at real numbers. We're not going to be looking at numbers that are associated with I. So if you don't know what I is, it's the square root of -1, and if that seems weird or confusing or you have no idea what I'm talking about, that's totally okay, because we're not going to mention it here. I only mentioned it in the asterisks by way of sort of being complete, that we're only looking at real numbers today. So outside of the naturals belong to a larger set of numbers called the integers. And the integers comprise, of course, the natural numbers plus the negative natural numbers as well. So you can see here from our example, 0, 1, -1, 2, -2, etc. Next, we have the rationals. The rationals, we probably should call them, I think someone joked, we should call them rationals, because a rational number is a number that can be written as a ratio of two integers. So again, 1 over 2, 5 over 4, apparently 253 over 495, and so forth. We have a little detour here into the constructible numbers. And this collection here, you don't have to worry about too much. I throw it in again for completeness. A constructible number is any number that you can make from the sort of ancient Greek, something to write with, compass and straight edge. So square root of 2 you can construct with a compass, pencil, and straight edge. Phi, the golden ratio, that is, you can also construct from those simple sort of ancient Greek processes. And there is the proof that 2 is irrational is actually, it is very cute. In a rational number, so constructible numbers, constructible numbers include rational numbers, but constructible numbers don't have to. So again, both phi and root 2 are not rational. That is to say, they can't be written as a ratio of two integers. And the proof that the square root of 2 can't be written as a ratio of two integers is again, it's really short, and that's what makes it kind of cute. So moving away from our little detour, we're in the big number here of the big collection of algebraics. So the algebraic numbers are any number that is a solution to an algebraic equation. And I feel like I may have, in the interest of being super clear, what I want to point out here is that within each circle, each inner circle is sort of a subcategory of the outer circle. So natural numbers are part of the integers, but there are integers, of course, that aren't natural numbers, like negative numbers. Rational numbers, you need rational numbers they can be integers, right? Like 1 over 1 produces an integer, but 1 over 2 doesn't produce an integer. So rationals include the integers, but aren't entirely integers. Again, constructible numbers include rational numbers, but also include irrationals. Algebraics include everything inside these other circles, but also other numbers as well, including actually particularly the cube roots of things, cube roots, fourth roots, fifth roots, that kind of thing as well. And then outside of that, we'll go to the next category, which is, oops, let's try going the right way. Outside this category, we go to computable numbers. So outside of the algebraics then, so outside of this ring here, all of these numbers are no longer algebraic. That is to say, you can't find them as a solution to an algebraic equation. So for example, e and pi are not algebraic. Numbers that aren't algebraic, we have a little note here, are transcendental. That's the kind of really beautiful name, fancy name for them. Now, computable numbers include all of these in here, but computable numbers also include some transcendentals. So for example, even though pi and e will never be the solution to an algebraic equation, there is a way that you can tell a computer, hey, this is how you calculate e, this is how you calculate pi, and a computer will find it. Now, of course, they'll have infinitely long decimal places, so you'll never get perfectly spot on with pi or e, but you can get as accurate as you need to. And then finally, we are at everything. So this is all the numbers. All the numbers. So inside here, inside the reals, we have all of these other guys. And so anything inside this computable circle and so forth is computable. Everything outside is a real number, but it's not necessarily computable. I also have a little subset here. So computable basically means you can tell a computer to find it. It's kind of it sounds a little flippant or a little sarcastic, but that's as straightforward as it means. If a computer, there are some numbers that a computer cannot calculate, that if you want to know what that number is, you have to sort of kind of brute force work it out one digit at a time. There's no formula or program that exists to find those numbers. So those are kind of way out here, kind of on the edge. I have a note here too that there's also a class of numbers called normal. And normal numbers are, are a class of numbers where you can find any string of numbers you want within its length. So pi might be a normal number. Pi is, random digits all the way out, but you might be able to find in there whatever string. So if you want to find your name, turn your name into numbers, and then you can probably find your name in pi. If you want to find like your street address, anyway, any kind of random subset of arrangement of numbers you want to find can be found in a normal number. But it's very hard to find them. And they're sort of, the reason why I put it down here as a subclass is because like if we were to draw a circle of the normal numbers, it would probably look something kind of like this, where like you might be able to find a normal number inside any of these other categories. So that's why it kind of doesn't really belong in a beautiful circle like the rest of these guys. All right, so this is kind of where we stand with numbers here. So on to the next part, let's talk about big numbers, because I think that's going to be exciting here. So we're going to zoom into this little guy right here. We're going to sort of zoom in and look at the integers now. So get rid of all that other stuff. We're going to focus on integers now. Let's review really quickly how we get big numbers. So we're going to use Donald Knuth's arrow notation. So here you might already have, just by seeing this, you probably already have a sense of how it works, right? 3 arrow 3 means 3 raised to the third power. So 3 times 3 times 3. We're going to use a little bit of nomenclature here for a little bit. So this guy here, this first number is called the base. And this number here is called the power. And I'm kind of embarrassed because I have to sneeze. Hopefully it won't interfere with the little chat here. Uh-oh. I wish we could take a second take, but we can't. So anyway, this guy here is the base and this guy's the power. So 3 arrow 3 means 3 raised to the third power. And the answer, of course, is 27. Next we have 3 double arrow 3. And this means take a string of single arrows and stretch them out for 3 times. So this, now you notice here that inside the parentheses, this guy is just this guy. They're the same, right? So this becomes 3 raised to the 3 raised to the 3, which means we end up with what's called a power tower. That's what this is right here. So this is a power tower of 3's that is 3 elements tall. And of course the answer is 3 to the 27. Now, you may already guess, this is actually a huge number, something like 7.6 trillion. So it's a big number. And you might be starting to see a pattern here. Next, we have 3 triple arrow 3. 3 triple arrow 3 means take double arrows and stretch them out. But we already know, right, this guy here is just the same as this. Which means it's the same as this. So this gets big really fast. This means that we're going to have 3 raised to a power tower of 3's that isn't 3 elements high like this guy. It's going to be 7.6 trillion 3's tall. So crazy, crazy big. Not the, and that number, that's just how you write the number. 3 to the 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 3, all the way 7.6 trillion times. That's not the actual number, that's just the shorthand for that number. And so the only answer you can say is that it's just stupid big. That's all. We don't know. It's huge. And we're going to keep sort of pushing this envelope. Let's go to 3 quadruple arrow 3. Now, I want to take a quick second and pause here why I'm using 3's here. This 3 quadruple arrow 3 is defined as G1. I know that seems like it's totally out of nowhere. So let me try to tidy that up here. With this base here and this power here, we can use any integer we want. We don't have to use 3. Heck, we can use any real number we want, really. We don't have to use 3. But to motivate the concept of a really big number that we're going to look at very soon, that big number begins with 3 in its base and actually has 3 as its power. So that's why we're using 3 on both ends of this, because it makes it a little easier to process later. So remember that 3 triple arrow 3 could be written as 3, as a stack of 3's, 7.6 trillion 3's tall. So 3 quadruple arrow 3 is even more ridiculous than that, whatever that ends up being. Let's look at the next number here. G2 is defined, so maybe you all have already seen this, but as a quick reminder, right, when we have an equal sign with 3 lines, that means defined as. I've heard some people say identical to, which might make more sense as well. But anyway, so an equal sign with 3 lines means this is defined to be G1. So G2 is defined to be 3, G1 number of arrows, 3. So I just want to emphasize that really quickly. Here we have 3 quadruple arrows, 3. Here we have 3 G1 number of arrows, 3. That's not the number of digits in the number. That's not the height of the power tower. That's just the number of arrows between the base here, between the base here and the power here. That's just the number of arrows. So this gets pretty crazy. And then we can proceed. G3 is defined to be 3, G2 the number of arrows, 3. And we do this for a while, and eventually, as time passes, we get to G64. G64 is defined as Graham's number. I haven't said anything about Graham's number. Graham's number was sort of first encountered in the 1970s, and at the time it was the largest finite number to be published in a mathematical paper. And it's the answer, it's the solution to a problem put forth in an area of mathematics called combinatorics. You don't have to know anything about combinatorics. And to me, the problem that Graham's number is a solution to is, to me, kind of boring. But if you are curious about how to solve, if you're curious about it, you can just look more up, read more about Graham's number. If you search for Graham's number, or if you search for G64, you'll find some stuff on it. So anyway, I just find it fascinating because it's like so stupidly big, ridiculously big. So just let's look at some other big numbers here. So these numbers, most of them that we're going to look at here are substantially smaller than Graham's number, but they're still big and they're still worth knowing about. So as you can tell here, this first one, all possible combinations of a Rubik's Cube, 4.3 times 10 to the 19 possible combinations. Now if your scientific notation is a little rusty, then just remember, so 10 to the 19th power means 10 multiplied by itself 19 times. So like 10 times 10 times 10 times 10 times 10 times 10 times 10, and I'm not going to go all the way to 19. But a shorthand way to think of this guy is that this guy here is really, if you were to write it out, it's really a 1 followed by 19 zeros. So if that feels a little weird, then you can kind of think of it as roughly 43 quintillion possible combinations. So 10 to the 19 is roughly 43 quintillion. All possible combinations of a Rubik's Cube. This next one here is Avogadro's number. This is the number of atoms in a particular mass of substance. So if you have 4 grams of helium, there should be exactly 6.022 times 10 to the 23rd atoms in 4 grams of helium, or in 12 grams of carbon, also the same number. So Avogadro's number is used in chemistry a lot to calculate amount of stuff. It also has the nickname the mole, M-O-L, and sort of like we think of the word dozen, like a dozen has like 12 things in it. A mole has this many things in it. Let's see here. Next, of course, are numbers that are very popular with children, Google and Googleplex. 10 to the 100 is a Google. That is 1 with 100 zeros. That's Google. Now, I want you to know this is not misspelled. Google, the tech giant, it was inspired by the name of this number, but this is how that number is spelled. Google changed the spelling on purpose. Actually, I don't know why they did. Anyway, so this is how you spell the number. And then, of course, 10 to the 10 to the 100 is the same as 10 to the Google, right? Because this guy is a Google. And so in other words, we have a Google right here in the upper 2 elements of this power tower. So 10 to the Google, which is also called a Googleplex. It sounds like a children's name. This is actually a real thing. You can look it up. This is neat too. This one I think is ridiculous. 10 to the 10 to the 10 to the 10 to the 2.08. This is called, as we have here, the Poincaré recurrence time. And according to some models in physics, the Poincaré recurrence time is the amount of time it takes before the universe kind of resets itself. Now, you might notice here that it's called the Poincaré recurrence time, but there are no units here. That's because this number is so big that it doesn't matter. In other words, this is 10 to the 10 to the 10 to the 10 to the 2.08. You want to pick seconds? Sure. That's close enough. Do you want to pick millennia? You want to pick millennia? That's fine. It doesn't matter whether it's seconds or thousands of years, or units of millennia. It's the same number because this number is so huge that the difference between seconds and millennia don't matter. That just seems crazy to me. Anyway, it's not guaranteed. This is not like guaranteed, right? Just according to some models of physics, this is what we're looking at. Next, of course, is Graham's number, which we've already talked about. After Graham's number, there is tree 3. Now, tree 3 I'm just putting on here because tree 3 is so huge that it makes Graham's number seem like 0. And I'm just going to leave it to you guys. Oops, excuse me. If you guys are curious about tree 3, this is how you write it, because the actual number is, we don't know. It's too huge to process. And then finally, we have Ryo of a Google. Recall here, so this notation here, this is also this guy up here. Let's tidy this up a little bit. So Ryo of a Google is a number. This currently, as far as I can tell, Ryo of a Google is currently the largest number, that's the largest finite number that's ever been formally described. So essentially what Ryo's number is the instructions are take one number larger than the largest number that can be written using a Google symbols of first order set theory notation. Now, you don't have to know very much of what I said, but essentially it says what's the biggest number you can write with a Google symbols. Now, not a Google numbers, not a Google like 1, 2, 3, 4, 5, 6, 7, 8, but a Google symbols from set theory notation. And set theory notation is really valuable for writing very dense, complicated information in very few symbols, or the few symbols you need. But in this case, you don't need a few symbols. You need, in this case, you don't have just a few symbols, you have a Google of them. So what I just described was kind of strange, because what I just described were the instructions for writing the number. This number here is so large, this guy here is so large, Ryo of a Google is so large that if you knew what the number was, you would run out of time. This Poincare recurrence time would elapse before you finished writing Ryo of a Google. That's how big this number is. And not only is it so big, it also, there just isn't room. If you were just to write it down on blackboards, there is not enough room, enough blackboards in the known universe to fit this number. That's, to me, just nuts. So, a little trip down the crazy, weird alley of big numbers. Now, we're going to look at our last little project here, which is infinities. So before we talk about infinities, I want us to talk about cardinality. So cardinality is a big word. It's a kind of a fancy word, and all it means, well, all it means is how big a collection of things is. It's a shorthand saying of, yeah, it's a shorthand of how many things are here. So I have two sets here. You've already probably guessed, right? Four smiley faces and 4 monkeys. And the cardinality of both of these sets is 4, because we got 4 little guys here, 4 smiley faces, and we got 4 monkeys. So the cardinality of a finite set is just how many elements are there. And of course, each little monkey each little monkey is called an element. So there are 4 elements in this set, 4 elements in this set. So the cardinality of a finite set is just that, how many things are in it. Then we get to, but this is of course a finite set, but we really care about the cardinality of an infinite set. Now this actually isn't all that much of a jump from cardinality of a finite set to infinite set. So here I've just given us an example of the natural numbers, of course. So 1, 2, 3, 4, 5, and this goes on forever. In order to establish the cardinality of an infinite set, we basically just say, okay, well, let's take the set of natural numbers and let's pair, this is the set we want to know about, and this is the natural numbers. Let's just pair each one of these off with a natural number. And look, we can do that, which is kind of cool, which in this case it shouldn't be a surprise, right? The natural numbers should pair with the natural numbers. So, and this, you can just do this infinitely. So, which means that the cardinality of the natural numbers is infinite. Cool, great. Let's look at another set here. I thought I had that slide. I guess I didn't. Oh well. So the natural numbers, and let's go to the next one, which is the integers. Remember, the integers is all the natural numbers plus negative numbers. So look, we'll start with 0, 1, -1, 2, -2, 3, -3, 4, -4, 5, and so forth, all the way as far as we want. We can match each one of those up with a natural number. So 0 you can match up with 1. So in other words, 0 is the first guy, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, and so on into infinity. But this is kind of strange. What this means is that the cardinality of the integers is the same as the cardinality of just the natural numbers. In other words, confusingly, there are as many integers as there are natural numbers. I'll kind of let that sink in for a second. There are as many integers as there are natural numbers. They're both infinite. And they're both the same size of infinity. That's kind of cool. But it gets even weirder. Look, these are the rational numbers. And again, we have 1 over 1, 1 over 2, 2 over 1, 1 over 3, and so forth. This goes on forever. There is a way of ordering the rational numbers, so that way you be sure to catch every single possible combination of rational numbers that is available. And again, you pair each one up with a natural number. So, super weird, but the cardinality of the rational numbers is the same as the cardinality of the naturals. So the naturals, the integers, and the rationals all have the same cardinality. Even though there seem to be more rational numbers, you can pair each one up with a natural number. So the cardinality is the same size. So let's get a quick summary here. So we've talked about everything inside this circle here. So the rationals, integers, and naturals. The cardinality of this group here, that's a little messy, isn't it? The cardinality of these three groups of numbers are all the same. And you know what? It's actually true of the constructibles, and it's also true of the algebraics. And then here, so remember, outside the algebraics, everything in this area here, everything outside of the algebraics are the transcendentals. All of these guys here. So everything inside here has the same cardinality. You can pair every single one of these numbers up with the natural numbers. That's kind of cool. Outside of it are the transcendental numbers. And we'll get to those in just a second. Okay, let's talk about the cardinality. Oh, sorry. Now, oh yeah, sorry. Let's look at, I kind of threw myself off here. These are let's look at the cardinality. Now, sorry, we're going to ignore specifically transcendentals and specifically computables. So we're going to make our little jump here from algebraics to real numbers. Excuse me. So we're looking at all real numbers. Now this is a collection of a few kind of random numbers here. So I have the first 6 digits of a number. It goes out to infinity this way, and this list goes down as far as I want it to. That's why the little dots are there. So what we're going to do is we're going to see, okay, well, do I have all the numbers listed in this set? Have I really listed all the real numbers in this set? Well, maybe. I need to find a number. Let's double check. And here's a way that you can do it. I should be giving credit to Georg Cantor, who discovered this, way back in the turn of the 20th century. Cantor is his name, Georg Cantor. And he proved this with this kind of diagonalization process. So what I've done is I just circled these numbers, 0, 1, 9, 1, 0, 7. I took the first number, the first digit in the first number, the second digit in the second number, the third, fourth, and so forth, all the way down, and again, presumably to infinity. And that gives us this number. This is the same number as I just diagonalized, this guy right here. Then what Georg Cantor did was, once he had found sort of a new number, you just add 1 to every digit. So add 1 to 0, you get 1. Add 1 to 2, add 1 to 1, you get 2. Now in this case, 9 you just start over. So 9 becomes 0, 1 becomes 2, and so forth. So this gives us a new number, this guy right here. Now the question is this guy in our collection? Well, no. Because look, the first number is 0, but the first number here is 1. The second number in the second class is 1, but here it's 2. The third one, the third is 9, but here it's 0, and so forth. So this number is not included in the set of real, in this list that I have of numbers. So I should add it. All right, let's do that. In the next slide here, we're going to see, we're going to take this number and we're just going to add it to our list. Okay, good. Now we've done that. Then we do that again. And what Cantor proved was that you will never stop doing this. That is to say, with all the real numbers, if you try to pair up all the real numbers with a natural number, you will always be missing one. That is to say, if I have, let's say, I have, another way to think of it is, let's say I want to pair this first guy up with the first natural number. I want to pair this guy up with the second natural number. And I want to pair this guy up here with like the third natural number. What Cantor showed is that no matter what, I can always find a number between these two guys. Or I can find a number between these two guys. So I will always have to rework this and say, oh, okay, well, if I found a number here and found it here, then I have to rewrite my system now. So it's like, okay, well, then 1 is here, and this new number I found is now. That guy's now 2, and this guy is now 3, and the new number that I found between them is now 4, and then this one is now 5. And I can keep doing that. I can find a number between 1 and this new number here that I called 2. There's another one in there. I can keep doing that forever, which means that the set of all real numbers is infinitely unlistable. That is, it's so big that I can't even start writing the numbers down, because any place I start, I will already have missed some other numbers somewhere else. So what this means, so to bring this all home, then what that means is that the cardinality, what we're seeing here is the cardinality of the integers is infinite. the cardinality of the real numbers is infinite, but the cardinality of the real numbers is bigger than the cardinality of the integers, which means that this infinity, the infinity of the real numbers, is actually a larger infinity than the infinity of the integers. Super weird. So we call this, if you can't list it, we call this listable versus unlistable infinity. So listable means you can at least start doing it. This is the cardinality of the integers. And then over here, unlistable is the cardinality of the real numbers, as in we can't even start writing them down because we will always have to go back and get something, get one else. So let's bring it all home. I had these in here. There's probably some real numbers. There's probably some real reason why I did that. Oh yeah, that's kind of neat, but maybe I won't worry about that. Yeah, actually no, I will. Okay, so here's why. Anyways, so cardinality of the real number is bigger than the cardinality of the integers. Crazy. So, but what we've already shown though is that everything inside the circle, the algebraics all the way down, all of these guys here have listable infinities, and everything outside of here, so everything in here is listable infinity, and everything outside is unlistable infinity. So because this infinity is bigger than this infinity, this means that we actually don't know that many numbers. So this whole diagram here, this whole diagram doesn't really do it justice. It really should look more like this. That is to say, most numbers, so this little group here are maybe our naturals and our integers and our constructables and our algebraics and our computables. Everything else, there's just a little tiny niche. Most numbers we don't know. Most numbers are not computable and are transcendental, and we can't find them with a computer. Most numbers are like that. So we just know a little tiny blip of numbers. We actually don't know most numbers because the cardinality of the real numbers is so much larger than the cardinality of these subsets here, even though they're both infinite. So let's just bring it all home. So if I haven't totally led you off a bunny trail by now, just three things. We know basically an infinitesimal fraction of all the real numbers that are out there. Stupid big numbers may be stupid big, but they are still finite. That is to say, even Graham's number, even Ryo's number has a first digit, I should say. Even Ryo's number has a first digit and a last digit, even if it takes the Poincaré recurrence time to find out what they are. And then, of course, infinity comes in different sizes. So hopefully that maybe sort of pushed the bounds of a little bit of what we all know about kind of the extreme areas of mathematics. I found this stuff really, really fascinating. So yeah, hopefully just kind of, if you've learned anything here, maybe it's just kind of a refresher of what it's like to be a student and to be sitting in a class where you're like, wait, I'm not sure, like this is all brand new to me again. So yeah, thank you all for your time.